Okay, so we can start. Okay, welcome everyone to the second talk of the day. So it gives me immense pleasure to welcome to the talk. I would like to give a short introduction of Dr. Maji. Dr. Maji did his bachelor's from Calcutta University and his master's from IIT Bombay. He did his PhD under the guidance of Professor Kalyan Chakrabarti. He then joined Indian Institute of Technology, Gandhinagar, as a postdoc fellow where he worked with Dr. Atul Dikshit. He is currently working as an assistant professor in the Department of Mathematics, Indian Institute of Technology, Indore. We'd like to thank him for accepting our invitation to deliver a talk amid his busy schedule. Dr. Maji, the stage is all yours. Please.
Yeah, thank you. Thank you for your kind introduction. Okay. Can you hear me?
Yes.
Okay. So first, I would like to thank Professor Nayandeep Dekabadua and Professor Bipul Kumar Sharma for the kind invitation to allow me to speak on this special occasion. So we all know that all over India, people are celebrating 134th birth anniversary of Srinivasa Ramanujan. So today I'll be speaking on some beautiful formulae of Ramanujan. We all know that Ramanujan has done a lot of works. Okay, it's very difficult to cover all the area, but today I'll try to emphasize only few 4 or 5 formulae of Ramanujan. So let me begin with a little bit story about Ramanujan. So Ramanujan was born on 22nd December in 1887 in his maternal grandmother house in Erode. Erode is a district in Tamil Nadu, into a poor Hindu Brahmin family. So after a few months, Komala Tamal, his mother, with Ramanujan, they returned to Kumbakonam. So Kumbakonam, and at Kumbakonam, Ramanujan started studying all those things. Okay, he entered into a government college in Kumbakonam. Didn't qualify his college degree because he was totally devoted to mathematics. So he neglected all the other subjects. Okay. So at the age of 12, Ramanujan got a copy of S.L. Loney's Plane Trigonometry from his senior, and he solved almost all problems in it. Then at the age of 15, he borrowed a copy of G.S. Carr's A Synopsis of Elementary Results in Pure Mathematics. So these two books influenced Ramanujan a lot. So in G.S. Carr's book, it's not a conventional mathematics book. It's a collection of results, elementary results. So he mentioned many formulas in this book, but without proof. Okay. Then Ramanujan started solving all the results in this book. And at that time, he thought that I can also write a similar book where results he wants to mention it. And in the same fashion, he started writing notebooks. Those are known as Ramanujan's notebook. Okay. But a mathematician believed that most of the results in Ramanujan's notebook, he knew the proof. He used to do all the calculation in his slate and then he used to erase it. But of course, sometimes Ramanujan's intuition was there. Okay, sometimes he may not know the proof of some results, but most of the results, mathematician believed that he knew the proof of his results. Okay, here's the picture from Ramanujan's notebook. Okay, this is this original copy is present in University of Madras. Few years back, Tata Institute of Fundamental Research, they published this book in a good form. So here is I have the two copy. Okay, I took picture from these two copies. So those who are really interested to know, to do work in mathematics, and even if you do not work in the area of Ramanujan, still I will encourage students to buy this book. Okay, you will definitely will get motivation from these two books. Okay, so today I am going to cover five topics. First is magic square, which is the chapter 1 of this volume 1 of Ramanujan's notebook, as well as chapter 1 of volume 2. And then I'll talk about a rapidly convergent series for 1 by pi. And then a Taxicab number, which is quite famous number. So most of you may know about it. And then one surprising identity I'll mention. And at the end, I'll mention a Ramanujan tau function. So magic squares. So magic square has a lot of history, like even in ancient India, ancient Chinese literature, as well as in the Egyptian literature also. People found the history of this magic square. People used to write down this magic square in temples. Okay. So the property of magic square is that, like here is a square, 3 by 3 square. You can see Ramanujan, this was the first chapter. So like at the age of 15, 16, Ramanujan started writing all these things. Okay. So this is the first chapter from his, this is the handwriting of Ramanujan. Okay. I took picture from the first page. So here he mentioned that this is a magic square where the entries are basically 1, 2, 3, 4 up to 9, 3 by 3, 9 places are there. But see, the sum of first row is 6 plus 1 is 7, plus 8 is 15. Similarly, sum of the second row, 7 plus 5 is 12, plus 3 is 15. Similarly, the sum of the third row is also 15. Sum of the first column is also 15, second column as well as third. Not only that, sum of the diagonals also, that is also 6 plus 5 is 11, plus 4 is 15. Okay, similarly, this diagonal, sum of the diagonals is 15. So one can ask that how many such magic square, 3 by 3 magic square can you construct with these numbers, 1, 2, 3 up to 9. So one can prove that this is only one possible. Okay. So here he mentioned another magic square. Okay. So here is a magic square with Ramanujan's birth date. 22nd December is 12, 1887. Okay. So I'll encourage students try to make one magic square with your birth date. So it is not so, it won't be that much difficult. I'll explain you how to do it. So that is the procedures of Ramanujan. I will explain that. So here for this, sum of each row as well as sum of each column and sum of the main diagonals and the sum of the 2 by 2 neighbor square. So this square, so all of these are equals to 139. Okay. So here Ramanujan gave an idea how to create such magic square, 4 by 4 magic square. So you first choose A, B, C, D 4 numbers and P, Q, R, S 4 numbers, and you put first in the diagonal. Okay, like some of you may have played Sudoku game, right? So Sudoku, like in Sudoku, the rule is like once you put A in the first row, then A won't appear once again in the same row. Okay, so similarly, you can see that all this A is appearing once in the first row. Similarly, B is also appearing once in the first row, C is also. So all these letters are appearing once in each row as well as once in each column. Okay, so if you like this 1, 2 position, like A and B is there. So AB cannot come in this position. So it can be C or D, right? So if you know the rule of Sudoku, then you can try to create. It won't be that much difficult to create this kind of magic square. So, so suppose you want to create a magic square with 22. First row is your 22, 12, and 1887. So then you first fixed A, B, C, D, four numbers, and P, Q, R, S, some four numbers accordingly, and then you try to fill up these entries. Okay, so I hope it is clear. So Ramanujan never stopped like at one point. So again, he mentioned that the similar way you can construct 5 by 5 magic square. Here also you can see in the diagonal A, B, C, D, E, and then P, Q, R, S up to T. And then using the same rule, he has created another magic square. And at the end, you can see he has written that similarly, we can form squares containing more rows and columns. Okay. So here is another magic square he has given, 8 by 8 magic square. Now, I'll mention a few open problems from inspired from this magic square. Okay, so using these numbers, I have already mentioned that 1, 2, 3 up to 9. So there is exactly one magic square of order 3 cross 3. Okay. Now you may ask that how many magic square can we form with the using the numbers 1, 2, 3, 4 up to 16. Okay, so 4 by 4 magic square we are talking. And that number is 880, quite big, right? Again, the number of magic squares of order 5 cos 5 is this much big number. Okay. So what will be the next natural question? So this is the for n greater than 5, using these numbers 1, 2, 3 up to n square, how many magic squares are there of order this n cross n? So this is still not known. So to solve this kind of problem, of course, now you may require computation. Computational knowledge is required. It's not so easy to find out the exact number of magic squares. Okay. Okay. So then magic square of squares. Okay. Now the entries are a square of some numbers like 4, 9. 4 is a 2 square, 9 is a 3 square, and so on. So in Martin Lover in 1984 asked, can you construct a magic square with squares? So that means entries are special kind of numbers. Those are entries are must be squares of some numbers. Then later in 1996, Martin Gardner offered $100 to the person who will construct such a square. In 2005, Christian Boyer offered €1,000 and a bottle of champagne for a solution of somewhat easier problem. So Ajay Chaudhary found a magic square of square. So here you can see the entries are squares of some numbers. Okay, but as I said, like solving this kind of finding this kind of magic square, it won't be that much easy. You need quite a computation and theory is required. Diophantine equation is required. So Ajay Chaudhary, he in his full life, he served as an Indian Foreign Service, but still he was interested in mathematics. He has published, I think, more than 90 research paper in reputed journal. Even now, he is doing research in this area in number theory. So here are the few references. Okay. Those who are interested in magic square, they can see these references. So here I have mentioned chapter 1 of Ramanujan's notebook, volume 1, as well as you can see in volume 2, chapter 1 of volume 2 is also devoted to magic square. Okay, now I'll talk about Madhava Leibniz Gregory series for pi. So pi, all of us know it's a quite important constant. Now, pi is its definition is it's a quotient of any circumference of any circle and its diameter. Okay. So pi has a lot of history. So the first exact formula for pi was given by Madhava in around 1400. So pi by 4 is quite a simple representation, right? Pi by 4 is 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on. And later, Leibniz and Gregory, they rediscovered this series. So it was quite challenging to find the exact value of pi. So we know that pi is an irrational number. So the digits of pi, they are not in a pattern. So that's why people were interested to find the digits of pi. And to find the digits of pi, this kind of formula was important. But this formula was quite slowly it converges. Okay. Now, Ramanujan produced many innovative series for computing pi, and one of the famous formula of Ramanujan is this one. It looks quite complicated, but it is quite important formula in this area. So here is a picture in Switzerland. There is a metro station, and metro station. This picture was there. So this picture was shared by Professor Frank Garban. So later, inspired from this Ramanujan's formula, like in this same paper, Ramanujan gave many around 17 formula for 1 by pi. So I have mentioned only few. Okay. And the last formula, which I have just now I have mentioned, that is the last one. Okay. So if you rewrite we can rewrite in that form. Okay. Then, as I said, like inspired from Ramanujan's work, then many mathematicians worked in this area, and one of the famous work of this Chudnovsky brothers, David and Gregory Chudnovsky, they discovered following variation of Ramanujan's formula for 1 by pi. And this here also these terms are looks a little complicated, so even if you do not understand these formulas, don't bother, just try to see it. So here is the picture of these two brothers. Okay, so more generally, people studied this formula for 1 by pi. People observed that this kind of behaviors are there. Like for 1 by pi, it can be written like k equals to 0 to infinity, s of k. What is s of k? S of k is involving some binomial coefficient. It satisfies some recurrence relation. Okay, and a, b, c, they are some constant. Okay, let me go back and try to show you. Okay. So here you see sk is basically this kind of 6k factorial by 3k factorial. So these are all binomial coefficients. And this is like a constant a plus b times k. And in the denominator, I mentioned c times c to the power k. Okay. So this is the more general form. So this kind of series is known as Ramanujan-Sato series. So many mathematicians discovered Ramanujan type series, and it is connected with the theory of modular forms. And Professor Berndt and Professor Bruce Berndt and Professor Barua also did a lot of work in this area. They also found this kind of series for 1 by pi. And this is all of you know Professor Baru. And this picture, actually, this picture I took when he was giving, Professor Burnt was giving lecture at Tezpur University. And I was sitting in the front bench, and during that time I took this picture. And Professor Burnt is one of the world foremost authority in the work of Srinivasa Ramanujan. And you can see he was wearing a t-shirt with Ramanujan's picture. Okay, so here's a few references for calculating regarding this. So here's the paper of David and Gregory Chudnovsky. And here's I have mentioned paper of Professor Barua and Professor Byrne. So this is a quite famous paper. So those who are interested in this area, they can have a look at this paper. This Okay. Now I'll mention Ramanujan taxi cab number. So, all of you know that Ramanujan went to Trinity College and he worked with RD for almost 5 years. Okay. So, during his stay, Ramanujan got ill and he was hospitalized. Okay. So, then G.H. Hardy once written that I remember once going to see him when he was lying ill at Putney. I had ridden in a taxi cab number 1729, that was the number of the taxi cab, and remarked that the number seemed to me rather a dull one, and that I hoped it was not an unfavorable woman. Then no, he replied, Ramanujan replied, it is very interesting number. It is the smallest number expressible as the sum of two cubes in two different ways. It is the smallest number expressible as the sum of two cubes, okay, in two different ways. Okay. That means 1729 can be written as a cube plus b cube equals to c cube plus d cube. Okay, a, b, c, d are all different. So here's the picture from I took from the man who knew infinity. So I think most of you may have seen. So those who have not seen this movie, I encourage you must see this movie. So here's Dev Patel who played the role of Ramanujan, and Jeremy Irons who played the role of G.H. Hardy. So here's the 1729, and 1729 is 1 cube plus 12 cube is equals to 9 cube plus 10 cube. Okay. So one can ask that why this is the smallest number. Okay. So you can check, like you calculate this way, 1 cube plus 2 cube, see that number, and can you write that number again in two different way. In that way you have to check it, and then you will see that this is the smallest number. You can write in two different ways. So now in Ramanujan's Lost Notebook in page 341, so Ramanujan's Lost Notebook, so these two books I have mentioned are known as Ramanujan's Notebook, and here is this one is known as Ramanujan's Lost Notebook. Okay. So lost notebooks are basically collection of loose papers. Okay, and these loose papers were lost for more than 50 years. Okay, like it was in Trinity College library, and Professor George Andrews, he is also one of the foremost authority in the work in the area of Srinivasa Ramanujan. He rediscovered this Ramanujan's lost notebook, and he coined this name. Okay. So in this book, in page 341, you can see this formula here Ramanujan has written. Okay, like this is a left hand side is quotient of polynomial. If we can write this as a0 plus a1x plus a2x square and so on, and similarly quotient of this two polynomial is writing b0 plus b1x plus b2x square and so on, and another expression, okay, where c0 plus c1 plus c2 x square and so on. Then Ramanujan wrote that this ai's they satisfy this relation. Then an cube plus bn cube equals to cn cube plus minus 1 whole to the power n. And similarly for alpha I, beta I, and gamma I, they also satisfy this relation. Okay. So here's I have taken picture from this Ramanujan's Lost Notebook, and you can see here in the corner, you can see in Ramanujan's handwriting that 9 cubes plus 10 cube equals to 12 cube plus 1. So Ramanujan knew about this number. So this number has came in his during his his research. Okay. So Ramanujan not only this kind, only these two. So here he has mentioned more such solution. Okay, like you can see that this big numbers he has written already. Okay. Okay. So now so from this work, now people are studying more a generalization of taxicab number. Okay. So taxicab k comma j comma n is the smallest number which can be expressed as the sum of kth power of j positive integer in n different ways. So let me explain once again. Taxicab of k comma j comma n is the smallest number which can be expressed as the sum of kth powers of j positive integer in n different ways. So let me give you some example, then it will be clear. Okay. So it will be sum of 1th power of two positive integer in two different ways, right? Taxicab of 1 comma 2 comma 2 means, so that is nothing but 4. 4 can be written as 1 plus 3 as well as 2 plus 2, two different ways. Sum of two numbers. Similarly, taxicab of 2 comma 2 comma 2 will be smallest number which can be written as sum of 2th power of two positive integer in two different ways, right? So that will be, you can check, it will be 50. Similarly, taxicab of 3 comma 2 comma 2 will be smallest integer which can be written as sum of cubed of two positive integer in two different, and that is nothing but a Ramanujan taxicab number, that is 1729. It can be written as a sum of cubes of two cubes in two different ways. So what will be the next natural question? Like taxicab of 4 comma 2 comma 2, what will be that number, right? What is the value of taxicab of 4 comma 2 comma 2? And Euler, he showed that this is nothing but this much big number. Okay. And he found this is the solution. Like this number is can be written in this way. Okay. Now, what is the next natural question? What will be taxicab of 5 comma 2 comma 2? Right? So even that is also not known. Okay, 5 comma 2 comma 2 or 5 comma 2 comma 3, these numbers are not known. So yeah, so when n equals to 2, we need to find a solution of this equation. X equals to a to the power 5 plus b to the power 5 equals to c to the power 5 plus d to the power 5. So this simple equation, still we do not know the solution of this simple equation. Okay, so here are the few references for this. This is a very famous book by Richard Guy, Unsolved Problems in Number Theory. Okay. Okay, now I'll mention this surprising identity. Sum of natural numbers up to infinity is minus 1 by 12. And similarly, sum of squares up to infinity is 0. And sum of cubes up to infinity is 1 by 120. So this may looks quite surprising, right? So it is, but in the left-hand side, always remember that this is the left-hand side expression is not the sum of the natural number, what we do in the usual sense. Okay, it has some different meaning. Sum of the natural numbers means not the usual what we do. Okay, I'll explain what do we mean by this left hand side expression. Okay, so let's see a proof of Ramanujan. So here he writes, let's assume C as this 1 plus 2 plus 3, 4 up to and continue. Okay. And then you multiply it by 4. Okay. In both sides. Then it will be 4C will be 4 plus 8 plus 12. Then he cleverly he put 4 below 2. And then he is placing 8 below 4, and then he is just subtracting from C to 4C, then he is getting minus 3C, and then he is getting this 1 minus 2 plus 3 and so on. And this alternating series he is writing in this way. But here little we cannot do this thing. Okay, this is not the proper justification. But here somehow he used the concept of analytic continuation. Okay, like this series can be written like in this way, but under analytic continuation. So in the usual sense, we cannot do such kind of operations. Okay, so let me explain how to what do we mean by this 1 plus 2 plus 3 up to infinity? Okay. And for that, we need to understand Riemann zeta function. Okay. So in 1859, Bernhard Riemann, he defined this series zeta s as the series n equals to 1 to infinity 1 by n to the power s. So this series is absolutely convergent for real part of s greater than 1. Okay. And this series defined analytic function in this domain. And Riemann proved that this function can be analytically continued to the whole complex plane, except for a simple pole at s equals to 1. Okay. So to understand analytic continuation, let me explain by this example. Like you consider this series 1 plus z square and so on up to infinity. Okay. This series 1 plus z square and so on up to infinity, this series is convergent when mod z is less than 1. But we can analytically continue, like this series is nothing but 1 by 1 minus z. And this function 1 by 1 minus z, this function is analytic in the whole complex plane except at z equals to 1. Okay, so that's why we call that 1 by 1 minus z is analytic continuation of this series. So similarly, Riemann found that there is an analytic continuation of Riemann zeta function. Okay, so for that function, we can talk about zeta at minus 1, zeta at minus 2, zeta at minus 3, and so on. Okay, so he showed that this beta function satisfies this beautiful functional equation. So this one is known as asymmetric functional equation. I haven't mentioned the symmetric functional equation. I should have mentioned it. That looks more beautiful. But now, once we have this functional equation, we are interested to know what is the value at zeta at minus 1. Okay, from functional equation, if you put s equals to minus 1 both side, then you can easily evaluate this, because sine minus pi by 2 is minus 1. Okay, and this constant gamma 2, gamma n is n minus 1 factorial, so gamma 2 is 1. And zeta 2, Euler has evaluated this, zeta 2 is nothing but pi square by 6. So if you just substitute it, then you will get zeta at minus 1 is minus 1 by 12. Okay, now we know that Riemann zeta function is absolutely convergent for real part of s is bigger than 1. We cannot put s equals to minus 1 here. But for fun, if we just substitute s equals to minus 1, then it will be what? It will be nothing but sum of the natural numbers. Similarly, if we put s equals to minus 2, it will be sum of the squares, right, up to infinity. So therefore, what we mean, like this sum of the natural numbers here, this is nothing but zeta at minus 1. And similarly, this sum of the squares up to infinity, this is nothing but zeta at minus 2. That can be also proved that, like, that is will be 0. Similarly, this is actually zeta at minus 3. Okay, so this is, always remember, this is not the sum of the natural number in the usual sense what we do. Okay. Okay, so here are the few references for this. Okay, so I'll yeah, I think I have 7 minutes.
Yes, Dr. Maji. You can actually continue up to 425.
Okay, yeah. Okay, thank you. So now I'll mention Ramanujan tau function, another interesting function. So Ramanujan first introduced this function in his famous paper on certain arithmetical function. So he writes this product, infinite product. Once you have an infinite product or infinite series, the first question is that whether this series is convergent, whether this infinite product is convergent or not. So for convergent, you require this mod q must be less than 1. And so here, this term 1 minus q to the power n whole to the power 24, this you can use binomial theorem. And then using that, you can write this infinite product as an infinite sum. Okay, then one can try to evaluate the coefficient of q to the power n for some small values of n. So Ramanujan did that. Ramanujan, I think up to n equals to 30 or n equals to 20, Ramanujan calculated values of this tau function. That means tau of 1 is 1, tau of 2 is something, some number, some natural number, or some, it may be some a negative integer also. So he calculated all these numbers, and then immediately he saw a pattern. Like he saw that tau of 6 is nothing but tau of 2 times tau of 3. Similarly, tau of 10 is nothing but tau of 2 times tau of 5. Okay, then immediately he conjectured that this tau function must be satisfying this first property. Then similarly, in the second property also he observed that. Now the third property was quite non-trivial, but this, he not only this, like more generally he conjectured that like tau of n must be less than equals to d of n times n to the power 11 by 2. D of n is the counts the number of positive divisors of n. And first two conjecture was immediately then in the next year in 1917, my model proved these first two conjectures. But the third conjecture took quite a long time, almost 50 years, more than 50 years. Pierre Delling, French mathematician, he proved as a consequence of bigger some other conjecture, Weil conjecture. And he got Fields Medal for this contribution. He also received Abel Prize in 2013. And there is many more properties in this paper Ramanujan established regarding this tau function, nice congruence properties. And there is a famous conjecture like that is known as Lehmer conjecture. Tau of n is never vanishing. Tau of n is not equals to 0 for all n natural number. So this simple conjecture is still open even today. Okay, so here's the picture of Pierre Delling. So I like this quotation. He said that I was not afraid to ask completely stupid question, and I have kept this habit until now. Okay, so Ramanujan, we know that Ramanujan like spent almost 5 years at Trinity College, and he was elected as a fellow of Royal Society, and then he was elected as a fellow of Trinity College as well. So here's the like in the middle you can see that Ramanujan is standing, and here's the here is G.H. Hardy, extremely right. Okay, so I'm going to end. So I'll mention a quote of Don Zagier. So one of the most romantic stories in the history of mathematics is that of the friendship between Hardy and Ramanujan. It began and ended with two famous letters. The first, sent by Ramanujan to Hardy in 1913, presents its author as a penniless clerk in a Madras shipping office who has made some discoveries that are termed by the local mathematician as sterling. So he has shown like his formula to local mathematicians, but local mathematicians were not able to understand all of his results. Okay. Hardy spent the night with Littlewood convincing himself that the letter was a work of a genius and not of a fraud, and promptly invited Ramanujan to come to England for what was to become one of the most famous mathematical collaborations in history. The other letter was sent in 1920, also by Ramanujan to Hardy, just 3 months before his death at the age of 32 in India. to which he had returned after 5 years in England. Here he recovers briefly from his illness and depression to tell Hardy excitedly about a new class of function that he has discovered and that he calls mock theta function. So people are like, this was in 1920, he has written this. But even after 100 years, people are still trying to understand what he meant by. Still, lot of research are going on in this area, but still people are not able to understand quite like what he meant by. So at the end, I'll mention this Freeman Dyson, a quote from a renowned mathematician as well as physicist, Freeman Dyson. I give thanks to Ramanujan for two things: for discovering congruence properties of partitions, and for not discovering criteria for dividing them into equal classes. So partition is another famous topic of Ramanujan, but I didn't mention that. So like Professor Barua, Professor Vipul Sharma, they are all are expert in the area of partition. So partition is a very nice function. Partition of n, partition of a natural number means how many ways you can write n as a sum of natural number in an increasing order or in a decreasing order. Okay, so Ramanujan gave few interesting congruence properties for partition. Okay, and he first he conjectured and then he proved also. Okay, but he didn't discover this criteria for dividing them into equal class, and that was done by Freeman Dyson when he was just 16 years old, and that was his first paper of Freeman Dyson. Okay. So that's why he is writing this. That was the wonderful thing about Ramanujan. Okay. He discovered so much, and yet he left so much more in his garden for other people to discover. In the 44 years since that happy day, I have intermittently been coming back to Ramanujan's garden. Every time when I come back, I find fresh flowers blooming. Okay. So with this, I'm ending my talk. Thank you for your attention. If you have any question, please feel free to ask.
Thank you so much for that wonderful talk. I'm sure that the participants learned a lot from this talk. So now I'd like to request the participants to ask questions if they have any.
Dr. Mazi,
Yes, yes,
oh, uh, you just mentioned that page of Ramanujan's notebook.
yes,
So it is the sum of the natural numbers is minus 1 by 12.
yes, yes.
So in that page, wasn't he doing infinity minus infinity?
Yeah, like yes, exactly. Infinity minus infinity. We can see, but he was like he. That is the thing. He didn't bother about like this convergence, all those things. Okay, whatever came in his mind, he was doing it. Okay, like he knew about Riemann zeta function, all those things, but somehow in a different way he got it. Okay, like he has done a lot of work like uh, in Riemann zeta function, but somehow he like he didn't thought that this is nothing but zeta minus one. Okay, but later people realize that it's nothing but zeta minus one. Yeah, but what Ramanujan was doing, that was like in a conventional sense we will say that it was not right. Okay, but that's how he got it, and but at the end he got the correct result.
Okay. And we have NDB sir also here with us. Nandi
Okay.
Borosa also with us.
Yes, yes, yeah.
Sir, if you have any comment, please.
Yeah.
Any comment or thank you to Bibekananda.
Yeah. Thank you to both of you. Yeah. Yeah. It was like I always like I have been to Tezpur University. I liked a lot like during my PhD. Okay. In future, I love to visit the campus, your campus. Yeah.
Okay, let's thank Bibekananda Maji from IIT Indore for being here with us and presenting so nicely about beautiful things about Ramanujan, starting with magic square of the partitions. So, a round of applause for Maji sir.
Thank you.
Thank you very much.
Thank you, all of you. Yeah.
So now I request Dr. Bipul Kumar Sharma to convey the vote of thanks. Sir, please.
Actually, I have thanked my speakers, Dr. Manjul Padim Sakya, as well as Dr. Bibekananda Maji, for giving their time to this session. And we must thank the scholars and students who are present over here to listen to these talks. And they have been participating in other activities also throughout the day. And Maji sir would like to hear that in the first half, we have conducted one quiz for the school students, as well as few games for the students of some schools nearby. So with this, we come to the conclusion of the National Mathematics Celebration at Tezpur University. Thank you very much.